Before proceeding to section 3 of chapter 3 on the topic of cubic splines, which is another approach to interpolate data, I wanted to return to the brief discussion on the tabular approach to generate the divided differences that are used to produce the a sub I coefficients for the Newton interpolating polynomial. This, you'll recall, is the tabular format that's used when you take the data, in this case 5 data points, and you produce the sequence of divided differences. The first order divided differences, second, third, and fourth, and of course the diagonal form, as we indicated earlier, would produce the a sub I coefficients, which are defined, which are part of the definition of the Newton interpolating polynomial. What you may not realize, of course, is that Charles Babbage in the 1800s, actually around the late 1830s and towards the beginning of the 1840s, actually built his prototype engine, one of the first mechanical computers, to actually accomplish this computation, because for high-order polynomials, perhaps as degree as high as 13s, it was very tedious for humans at the time to be able to do these differences without making errors. And so Babbage actually envisioned a mechanical engine to actually do the computation for them to produce interpolated results. And his prototype engine didn't actually produce 13. I think he wanted to do as high as a 13-degree polynomial, but he only actually implemented 3 columns there, so it basically only interpolated up to about a cubic or a 4th-degree polynomial at most. And so it's an interesting part of history. When I teach one of the study abroad courses in our Engineering London program, we actually go to the British Museum and actually see the prototype engine that Babbage built to actually compute divided differences, so that polynomial interpolation could be done as early as in the 1840s by a mechanical engine rather than a human. So now we move on to the next section called cubic splines. As we recall earlier, when we interpolate with polynomials, the higher the degree the polynomial is, the oscillation effects of the polynomial through the data points can become a problem. The polynomial does interpolate to the data, but it wiggles and turns in ways that are not consistent with the trend of the data. What you see here is a very smooth function, indicated in green here, that interpolates the data points. The x-coordinates are running from x0 all the way through xn. And that's going to be very difficult to do with a single interpolating polynomial of fairly high degree that would actually fit all those data points. So the technique here is to produce this very smooth interpolant that doesn't oscillate between the data points, also known sometimes as knots when we're implementing what are called cubic splines. The idea here is that each of the interpolation is done by connecting up a series of polynomials. So each one of these components between each of the data points there is a different function. It's a different cubic polynomial. So what we have is a whole sequence of cubic polynomials that basically are just sort of attached to each other that match up on the data points, so that the indexing we use is fi, I plus 1 of x on the subinterval xi plus 1. So this first one, for example, would be f0, 1 of x. The next one would be f1, 2 of x, and so forth and so on, so that actually this last one here would be, say, n minus 1, n of x. So it's a way of us indexing all of these cubic polynomials. So this is what we could sometimes call a piecewise interpolating polynomial. It's not just one polynomial that fits all the data points, it's a sequence of cubic polynomials that are used to fit, but that can be constrained in a way to have this very, very nice smooth form. If you go back into the 1970s and perhaps part of the 1980s, if you are a drafts person, you are very familiar with the concept of a spline, especially in the automotive industry. It was before we had CAD systems and digital computers. The way that draftsmen could draw very smooth curves like this was to take on a board, insert certain pegs into the board, and then be able to take a very flexible piece of plastic and another point here, and move that plastic through those pegs. And that was the idea of a spline, so that it was very flexible and it could be bent through that, and that would be a way that they could do their curve drawings, for example, if they were trying to draw the design of an automobile in some sense, so that you would have this very simple way of getting smoothness for your design. But our approach here is to use mathematics. It's to use a computational approach to produce sort of splines rather than doing something physical. So the way smoothness is achieved is through the use of derivatives, especially the second derivative, it turns out. Now, there's a particular terminology that's used in the language of cubic splines, and that is what is known as what's called a natural cubic spline. It's the particular case where the second derivative for the very first cubic function at the initial point is 0, as well as the second derivative of the last cubic polynomial is equal to 0. Essentially, from a graphical standpoint, what that does is basically if we had a grid, which we've had on the previous slide, if this was x0, the first data point, and this is the x-coordinate of the last data point, xn, and you had all the interior points that we had before, I guess I won't draw them. Basically what this constraint does is it makes the spline sort of flat up to this x1 point, and then it goes ahead and interpolates very smoothly the data, and then when it gets back at the last point it flattens out again. Some people think of this as a way of maybe having like two hands at both ends of the spline, and it's sort of pulling them apart to tighten up the curve, so to speak. But that's the idea of that's the nature of what is meant by a natural cubic spline. The second derivatives at the end, if we force to 0, flattens things out sort of that way. So again, a spline is a piecewise cubic curve formed from n cubics. All right, each one of these f functions here are cubic, so the entire spline is a cubic. All right. So to get the curvatures within the interior points, what we want to do is this constraint. If we let k, capital K sub I, be the second derivative of the spline at not I, again, if we say xi, that's the same thing as saying not I. It's the same. It's just another way of saying x sub I. Curvature is another word for second derivative. So this is just some nomenclature that's used in this interpolating discussion that's consistent when you see cubic splines in literature. The constraint is that we want the second derivative on successive subintervals to be equal at a data point. So for example, if we go back to our grid, and this was xi minus 1, and this was the point xi, and this was the data point xi plus 1, or not xi plus 1, and this is not xi. What we want to have happen again is, remember this function here lives on this subinterval, this function here lives on that subinterval, and we want their second derivatives to agree on xi to be this point. So essentially what we have is an interpolation issue. So what we're trying to say is that we want on a given subinterval, we want to see two things happen. So if we specified, just for sake of the argument, let's just say xi and xi plus 1, if we just look at this particular function here, fi comma I plus 1, this cubic function is living on that subinterval. What we want to have happen is that when we compute the second derivative of this function, I comma I plus 1, we want it to be, when we plug in xi, we want to get ki, this curvature back. Okay? And then when we plug in xi plus 1, in other words, when we change this value right here, I'll move this over here, for example. We also want f double prime of this function, I, comma, I plus 1, on the endpoint of the subinterval, xi plus 1, to produce the ki plus 1 curvature. Okay. So essentially what we have is an interpolation problem on that subinterval for the second derivative. It's just the constraints to get smoothness. All right. So if we go to the next slide, given the constraints we want to have happen, then how can we construct what the coefficients of f sub I plus 1 of x to be? Well, again, if we have the constraint on the second derivative, then we can go back to, which I just showed you what they are, is that we want to, when we plug in xi to the second derivative on that subinterval, we want to get ki back, and then we plug in xi plus 1, we want to get ki plus 1 back. So we can result to Lagrange's two-point interpolation formula that we had before. Instead of using yi's, we're going to use the ki's, these curvatures, and then these are the forms that we had for the cardinal functions. In via substitution, you can easily show, if you go back to your notes, or our notes on the Lagrange interpolating polynomial, that's the form of the second derivative. That's what the second derivative would have to look in terms of the curvatures and those x-coordinates, the grid. We call those grid points, or knots, remember, on the real axis. So this is a form that the second derivative of these piecewise cubics are going to have to take on, and this is the one for the subinterval I, comma, I plus 1. So why did we care so much about the second derivatives? Again, it was to get the smoothness through the interior points. But what we really need to do is to be able to produce what the cubic spline is going to look like, so that we can use it to do predictions and to fill in missing values and so forth, just like we've done with other forms of interpolants. So what can we do? Well, we have a form for the second derivative on each of the subintervals. We would just integrate twice. So we would do an integration to get the first derivative, and then we'd integrate that first derivative. And what you see here is what that two process of integration would produce, with the fact that there will be two integration constants. And that answers this question: where did the constants come from? Well, remember, when we integrate, we would have a constant each time, and we're going to call them A and B. This is the form of what each of the cubic polynomials on each subinterval, in this case, again, this is the function that lives on xi, comma, xi plus 1. It lives on this subinterval. This is the form it would take. All right. So we can now construct each cubic polynomial that defines the cubic spline. They are potentially different because they depend on where, the values of the subinterval itself and these curvatures. And again, what our goal is to come up with a complete formula that will produce a very smooth interpolating polynomial through the data. So, given we just said that, we have to remember that the spline also has to interpolate the data. In other words, when you plug in xi into its appropriate function, you should get yi back. So keep in mind, on this grid, right, starting from x0, x1, and so forth, all the way to xn, and maybe we could write the previous one before that, xn minus 1, the spline has a different function or formula on each of the subintervals. So when you want to evaluate a particular value, in other words, for x1, or you want to plug in xn minus 1, you have to use the appropriate function. All right. Again, the one that lives on this subinterval is called f comma 0 comma 1 of x. So when you plug in x1, for example, into this function, you better get y1 back. It needs to interpolate the data. Exploiting that fact and going back to the original equation you had in the previous slide, we go back to this equation and you plug in x I or I plus 1, depending upon what you want to, either one, some of these terms are going to go away. For example, if you plug in xi, notice this term is going to go away completely, as will this term as well. Okay? So what will happen is when you plug in xi, several terms go away, and this is what you're left with. All right? So now, if you look at this carefully, we have a way of defining what that a should be, because we could solve for a, and we know explicitly what that constant would be. That was obtained through doing the double integration. What happened to the b term? We just said that. It was eliminated because it was be multiplied by the term x minus xi. And when you plug in xi in for x, that term becomes 0. Well, on that same subinterval, if you go on the right side of the subinterval, when you plug in x plus 1 in to that function, you should get back yi plus 1. Again, go back to the original form of the representation of this function fi plus 1 that had the two constants a and b in it. When you plug in xi plus 1, it eliminates all the terms that had a in it, and now we have a representation of an equation that involves just the x coordinates, the y coordinates, the curvature, and b. So therefore, you could then solve like in the previous slide for a, and now we know exactly what that constant looks like, and now we know exactly what the constant b looks like. Yes, this is kind of messy, it's kind of complicated, but it's just simple algebra using these constraints on second derivatives is where all this came from, to try to make sure that the cubic polynomials smoothly transcend from one subinterval to the next. So when you put all the pieces together, substitute what we just said the integration constants would be, what you see here is a complete description of what each cubic polynomial that defines the overall cubic spline should look like. So remember, it depends on where you are on the mesh, because each one of these f's depends on where you are in terms of the xi plus 1 and the xi's, as well as the corresponding data y coordinates, yi and yi plus 1. So this is the general formula to define each of those cubic polynomials. As indicated in the next slide, the continuity constraints for cubic splines don't just apply only to the second derivative. We also want continuity in the slopes on each of the subintervals, i.e. the first derivatives. So we want, for example, f prime of xi minus 1 comma I at xi to be the same as the derivative on the other side of that xi point involving the next cubic polynomial. So, so as we move from one subinterval to the next, we want the derivatives to be the same at the adjacent points, right? And in particular, we're only looking at the interior points. So we're only looking on the mesh, not at x0 and not at xn. We're trying to make sure that the first derivatives match at x1, they match at x2. In other words, that the derivative coming in here, for example, is matching the derivative coming out there, and so forth. So we're trying to make a very smooth kind of transition on the interior points. So then you could go back to our equation that we came up with in the previous slide for the cubic polynomial on each subinterval, namely this one, differentiate this form with respect to x, and if we do that, you would actually get a linear system that would look something as defined here. You would get a constraint that involves the k's, all right, on the left-hand side of the equal signs, and then all these terms on the right which involve your x and y coordinates. Now, the question here is, all right, we did all this construction. We know what the xi's are. We know what the yi's are. That's the data point we're given. I never told you exactly what the curvatures were. We just said let's assume what the second derivatives are and called them ki's and ki plus 1 and so forth. This actually tells you exactly what those curvatures should be from the construction we did. If you think the fact that all of these subtractions here are just scalar values, so these are all scalars, because that comes from the data points that you're given. This is a complete scalar. The k's are what are unknown. But if you notice the fact that they're always consecutive in terms of the indexing, ki minus 1, ki, and ki plus 1, this coefficient matrix that we would be constructing would actually be a tridiagonal matrix. So it's interesting that to construct a cubic spline actually involves solving a tridiagonal linear system of equations for these curvatures, which were assumed to exist in defining the continuity from one of the cubic polynomials on one subinterval to the next. So it's using all the things we've talked about before in terms of special forms for linear systems, and this shows you that it's because of the adjacentness of the subintervals and wanting these first and second derivatives to be continuous at those interior knots forces this linear system of equation to be true, to hold, and what we end up doing is solving this tridiagonal system for the case of i's. Now, if the knots are equally spaced so that every time you move from one knot to the next, you travel the same distance. So in other words, if the distance between x0 and x1 on the grid is distance h, and then you go another h distance for x2 and so forth, then of course we could say, well, that would mean that the difference between xi plus 1 and xi is h. That linear system would simplify much easier to much easier form like this, all right? And it's just an easier way to represent that linear system and very much easier to solve it. So we'll next look at this Python script to produce a cubic spline for interpolating data, which comes on page 122 and 123, and then we'll look at an illustration of its use in example 3.7 on pages 123 and 124. I will put these modules out on Blackboard for you to use and to test with. Again, a very nice piece, compact code that is going to end up solving a tridiagonal linear system of equations for those curvatures. And you'll see that if you draw or plot the particular cubic spline, you'll see how smooth it fits through the data that you want to interpolate. So if we go to the textbook and look at page 122, you will see the cubic spline Python script. Again, the module is called cubic spline, and what you'll see is that there's a couple of functions that define the module. The first one is called curvatures, because again, given your data that you want to interpolate to, x data, y data, you need to produce those case of i's, the curvatures for the cubic spline at all the knots. And then once you have those curvatures in that array k, that's fed into a function called eval spline that will actually evaluate the spline depending upon the value of x that you give it. So you need your original data again, x data and y data, and you need the curvatures produced by this function, and then say, where do you want to evaluate the spline? Any data point on, hopefully lies somewhere in the mesh between x0 and xn. If we look at some other components of the code, it's again using NumPy. Remember, to get the curvatures, you're solving a tridiagonal linear system, so we have seen LUD-comp3 before. You have that module available. It's on Blackboard, so we will need to use that. So here's what the function, the curvatures function is doing: initialization of several arrays, setting up the tridiagonal linear system, and then solving it. So it has to decompose it, get the LU factor, and then use the LU factor to solve it. So for our purposes, all you need to realize is that this will get those curvatures that you wanted. It's basically solving the linear system that we constructed in the notes. And then you actually evaluate the spline using this other function called eval spline. So if we continue on the next page, again, it has to figure out where that x, the subinterval that x lives on, because as I said earlier, this spline is a sequence of cubic polynomials. You have to figure out where it lies, and then once you know which subinterval it lies in, then you can evaluate that particular function. And then then go ahead and take that and plug it into the formula that we had in the notes for the cubic spline, and that's what this is doing there. We continue on to this example, and I will demonstrate the code for you and provide it on Blackboard. Here is a problem where you have this set of data, the Cartesian coordinate system. You have these x coordinates and y coordinates, and you would like to build a natural cubic spline to determine what the spline would be at, say, 1.5, which certainly is somewhere between 1 and 2, between knots 1 and 2. And you'll notice that as you travel along the x-axis, everything's at a distance h equals 1, so you have that very nice form for the linear system that we had in the notes. But the code that we gave you is general enough so that it doesn't really matter what the space in the knot is. It doesn't assume, the code does not assume that they're equally spaced. This is just an illustration of producing the cubic spline that goes to the data. We wanted to know the particular value of 1.5. It turns out to be 0.7679. But then if we take and evaluate the cubic spline at several points on the mesh between x0 and xn, you can see, in fact, it's cubic in nature and very, very smooth, because the data points were at, if we go back to look very carefully what the mesh was, the data points were 1, 2, 3, 4, 5 on the x-axis. And so what that means is that between 1 and 2 is a cubic polynomial, between 2 and 3 is another one, 3 and 4 is another one, and 4 and 5 is another one. But the continuity constraints force things to line up so that you might think this is actually one cubic polynomial because it's how smooth it is, but in fact it's a sequence of 4 cubic polynomials. So I'm going to pull the code out and illustrate and run it for you so you'll get a sense of how this is going to work for you, because you're going to find for the homework that we're going to do with using splines, the smoothness is going to be very, very useful for the application that we're going to ask you to do. So here I'm showing you the example 3_7.py file that I will post on Blackboard for you. So this is solving that problem in the book using Python, knowing that we use NumPy to manage arrays. We're going to use 64-bit arithmetic or double precision for this problem, and many interpolation problems. Sometimes it's important to use higher precision. We're going to use our cubic spline module, use all the functions in there, and because we're going to plot, we'll use matplotlib, and one way of specifying it would be using an import statement like this, because we want to use pyplot and just use an alias for the pyplot as plt. So it'll be a simpler way of using all the functions that are available in matplotlib for drawing, curve drawing. So we would take the data that we had from that problem, passing those appropriate lists into the array function. So we'll build an array for x data and y data. We're going to specify double precision, in this case 64-bit arithmetic, and that's how you would do that with the float 64 data type. Again, because we're using the cubic spline module, we're going to call the curvatures function it provides so we can get our curvatures. And then here's the generation of a mesh, so that, keep in mind, this is the data we interpolate to. These are the x and y coordinates, but we want to draw the cubic spline for many points, not just those. So one way of doing that is we'll build an array that will run from 1 up to, but not including 5.1, in increments of a tenth, and that's what this line is doing right here. So that's going to give us a nice little mesh running from 1 to 5 in increments of 1 over 10, and then we'll take each of those points and evaluate the cubic spline at it. So that's why we're calling eval spline with x data, y data, and the curvature at x of I, where the x is the array I'm generating for the mesh. The length of it is n, so that tells me exactly how many data points I'm going to generate. I'm going to generate a yi for every xi. And then after I do that, I'll just use the plot function to plot the data. I'm going to use a blue curve. I want to show the graph in a window. I'm going to title it. You can put a title on the graph this way, and I can label the axes with just simple strings x and y. So that's it. It's very simple. It's a very elegant way to take that data and draw a smooth curve through it. So this is one way you can think of doing a very primitive form of computer graphics, that I give you some data points and I want a smooth curve through them. So we just execute it, and of course you have to make sure that you have all those modules available, NumPy as well as Matplotlib, and we just type the code. I'm running this remotely on a different machine to display on my laptop. Let me move the figure over, and in fact here is a very relatively smooth. There's maybe some issues here with smoothness. We could have added maybe some more points around 3 and around 2 and perhaps 4 to smooth that out a little bit. But in general, it does a pretty good job of interpolating the data that we get and generate a curve similar to what we saw in the book.